Okay, I'll turn it over to you.
Yep, so I'm just waiting for, all right. So hello everyone, once again on this Thursday for Models 2020. It's my pleasure to present to you our keynote speaker for today, Betty Cheng. Betty's a professor at Michigan State University, where she works on various topics on dynamically adaptive systems, requirement engineering, MDE, and automated software engineering. Betty has a stellar research track record rewarded by several awards such as Distinguished Faculty, Scholar, Teaching Awards from MSU, and multiple Most Influential Paper Awards from Models, RE, and ICSE. Betty is one of the few researchers I know who extensively works with industry as well as distinguishing herself in the classroom. She manages projects funded by NSF, DARPA, the automotive industry with Ford, GM, the aerospace industry, NASA, and the telecom industry, Motorola and Siemens. Betty's very involved in the scientific community, especially in models, as you all know, many of you know her, being the also associate editor-in-chief of the prestigious journal TSE, on the program board of many world-class conferences, and organizer and chair of many other international events. Today, I'm really looking forward to hearing your experience on vision on mixing data and models in the engineering of autonomous systems. So Betty, the floor is yours.
Thank you, Eugene. So I hope I set the tone for the talk. This is sort of, I want this to be a bit of a break from all of your Zoom overloading. So we're gonna have fun with this and we'll see, hopefully we can learn something from each other. So let me go ahead and I will just tell you, I'm actually sometimes Zoom challenged. I do want to start with expressing our collective appreciation to all of the frontline workers of the pandemic. I think that all of us have had various kinds of impacts of that. And so hopefully we can be thinking about them as well and think safe, wear your mask. I know that most of you do that already, but in the US, we still are struggling with that concept at this point. The preface for this talk actually is based on some work that we had done a couple years ago in sunny Barbados, and it has continued. So that's the theme for the music and also this work. And this is really looking at the interplay between models and data, and specifically not only at design time, but at runtime, and how could we build systems to be more reactive to that. So I'm going to share some some experiences that I've had and how it helped me to shape where I am today and how I look at these large scale systems that are data centric, but we are using model driven engineering to develop them. So this is the group of folks that, this is back in the good old days when we could actually enjoy and relax in person. So I think that just as a context, I want you to think about these model-driven data-centric systems. So these are some of the current systems that we are familiar with, whether it's smart grid systems or smart farming. I'm coming from the state of Michigan in the US, where we look at intelligent transportation and vehicle systems. So these are, all of these have the common theme of being autonomous or self-star. So they have monitoring what's going on around the environment and then are trying to be reactive to those purposes. So the challenge that we have is that as these systems become more complicated, how do we manage them, both in terms of the development, but also in terms of their runtime interactions? So I thought, well, what was the challenge that we were really looking at? Is in fact, when you build these complex systems, you are actually dealing with lots of different kinds of modeling techniques, whether they are at the system level, at the individual level, at the process level. But some of them are scientific models, et cetera. So one way to sort them out is to say, well, maybe there's two big classes or two big clusters of model types. Whether one might be the scientific models that describe sort of phenomenon for study, for understanding things like climate change, atmosphere, flood prediction. These tend to be continuous models. And then, on the other hand, you have engineering models, right, which is probably where most of us work. And these tend to describe your target system that you're trying to develop, with mostly a lot of the intent is actually to enable some kind of automatic processing. So whether it's design models for code generation and process models, etc. And so I thought this was an interesting quote, right, as far as how we might distinguish those two types of models and those two types of thinking. So, and then recently, it seems like for the last couple of years now, there's been a lot of attention afforded to this whole area of machine learning and AI systems. And I think that we also learned a lot more about that from our keynote speaker yesterday. But I think that in terms of the model itself, just to clarify, when you talk about machine learning models, the model itself is a result of actually applying your learning algorithms to some data where you're trying to recognize certain types of patterns. And then when you finally finish that application of the learning algorithm to your data, you can use that model now to make predictions, etc. So kind of keeping that as a backdrop, when we try to sort out this babble of models, the idea is maybe we can think about what the purpose, how we are using those particular models, right? So whether the descriptive models, and a lot of times that is really based on the kind of data that is actually being used. So descriptive data is using historic data to explain what happened, right? Predictive data, you're using historic data, you want to be able to think about what might happen when you actually see new data at runtime, right? Prescriptive data is really trying to talk about how you would actually go about achieving a particular objective. So the same thing with this whole notion of lots of different kinds of model types. There might also be lots of different types of data, right? How it's being processed by and produced by models. And again, similarly, there's lots of different types. So we have similarly this whole notion of this Babel Tower of data. So the question is then, if we can somehow take the model types and the data types and organize them according to the types of uses, the question is, can we take these two different types of Babel towers to be able to create our data-centric systems, right? We're looking at it from a model-driven approach. And so that's sort of my overall objective. And I want to share a little bit about my journey to get to this point where we're looking at these current data-centric systems. And a lot of this was, put in the context of the work that we did in our Barbados trip, is coming up with a framework for helping us to organize this all the different types of models and all the different types of data types, and also the synergistic interaction between those two. And so in our motor framework that we recently have published is really trying to distinguish these different types of models and the kinds of roles that they might play in these current day data-driven autonomous systems. And so that's something that I'm going to use as a backdrop. So if I don't get to the end of my talk, I'll give you the keynote, the takeaways at this point, right? And so hopefully at the end of this, you'll see that a lot of my work and the message I'm trying to promote is to focus on working on real world problems, right? And so that way, a lot of this stuff kind of comes naturally. And also about building bridges, right? Stepping outside of our comfort zone and outside of our silo-based views and trying to tackle these real-world problems. And that will necessarily, force us or encourage us to work outside the box, right? Because I think that we can make progress on real-world challenges by working outside the box. And those of you who've known me, my whole career has basically been focusing on assurance and all these different aspects of assurance. And so now I put in there assurance as if your life depended on it. And so hopefully you'll see some of the different application areas that I'm working on that hopefully you'll see why that assurance is so important. So my first bridge is that by coincidence, I'm actually between the two areas that I'm trying to bridge. So yesterday we had some really interesting perspectives and also some challenges from Yosha Bingio on some of the priors of deep learning and what are some of the challenges. And then Christoph Czarnecki is going to talk about how models and AI enabled systems are going to be used and can be used for autonomous vehicles. I mean, what are some of the challenges and how to overcome those? And so I'm really looking at sort of that space in between them, right? So this is conceptual as well as chronological. So I think that, as Eugene mentioned, so a lot of my work has definitely been flavored by my interest in working with industry. And as I said, life is short, so let's focus on some problems that actually will have some impact. And so a lot of that is my motivation to take what we're doing in academic research and try to understand, how they might fit in industrial settings, but more importantly, how industrial settings will color but not necessarily constrain what we do in research. In other words, we don't want to necessarily be contract workers, but we also want to know that the problems that we're working on are in fact relevant, right? And so that's been something that I've been very fortunate to have been working with industry throughout my career. And it's really, and the problems that they work on and the challenges that they have continued to make what I do extremely enjoyable and rewarding, both in terms of research, but also in the classroom. So I also bring the industrial perspective to my classroom. So the question here is that we found is that one challenge is the effective communication, right? There's a lot of complaints sometimes that, you know, we work in our ivory towers and so we don't really know how to converse. And so that was really one of my motivations. That in my original work, I was actually working in formal methods, and it turned out they were not interested in that at all. And so how do I extend that olive branch, or how do I get that bridge across to them? And that was where we really looked at sort of using model-driven engineering, model-driven development as a means to provide a path for them to go from what they know in terms of the informal model, graphical modeling, to something that I want to be able to do with respect to formal representations and reasoning, again, focusing on the assurance capabilities. And that's actually how my introduction into the whole models community was. And that was many, many years ago. So the other bridge that we're looking at is one of my first bridges that I think that was focusing outside of the box with respect to models, was looking at how software engineering, model-driven engineering could be applied into this area of environmental science, climate change, etc. And that what we had to deal with at that time was really looking at a disparate collection of environmental models, right? Looking at land use, climate change, etc. And we found that there was a broad range of stakeholders, right? And so the key thing is that they needed to be able to bring all that information together to make informed decisions regarding policy and land use. So I'm having a Zoom moment here. So this was actually a project, just to provide perspective, it's actually pre-web, but the idea was this was funded by NASA here in the US, the USDA, Department of Agriculture, Environmental Protection Agency. And they had lots and lots of data, right? They had just deployed this huge satellite, the Earth Observing System, and was downloading terabytes of data, all right? And they had weather data, they had georeference data, and they were trying to put all these things together to try to collectively make some decisions about how to you know, define policies for land use, how to define policies about how to manage water quality, right? And so this is something where I, even as an assistant professor, I was working with 22 different departments on our campus, working with 3 different federal agencies and trying to juggle a lot of information. And I was definitely outside of my comfort zone. So the question is, how could we try to bring together all these different kinds of models and different data to come up with this decision support system, or what we called informs? And so working outside the box, right? So the question is, one thing I'll preface this is that one of the side effects, as a side note, is that my son was home with me. He normally lives in school in New York, going to Columbia Law School. But one of the things he did was to pick up a hobby of photography. And so I'm going to interject a few pictures here and there just to kind of keep things different. So this is actually the George Washington Bridge from New York City. This is what he took last summer, well, before the pandemic. Anyway, so this was a bridge in trying to explore my disciplinary work. What kind of disciplinary are we looking at? Well, initially, it was truly just multidisciplinary. I'm working with lots of different people from different disciplines, trying to leverage their respective disciplinary expertise. I'm working with geologists, I'm working with social scientists, etc. So how do we come together to come up with this decision support system? So it turns out that we, you know, initially started out at the different disciplines, right? Lots of different kinds of data, right? Coming from lots of different owners, right? Whether it's federal agencies, research labs, etc. So the kinds of information that they are providing to us, they had all sorts of models. They were descriptive models, they were predictive models, they had policy models, right? And so how can we take all that, right, and actually be able to channel that into a decision support system? So I hear they have lots and lots of data. This is why the orange Babel Tower of data is much bigger than the models themselves, right? And so initially, the environmental scientists had lots and lots of data and their models. And the question is, how could they work with policy analysts, right, to actually come up with those recommended decisions? And so this is where the computer scientists, you know, myself and my team came in, and we said, well, can we somehow support some kind of interdisciplinary work, right, to actually encourage and promote synergistic integration of that information? So in other words, prior to that, you know, if you wanted to look at, you know, satellite imagery, you had to log into a satellite imagery data. If you wanted to look at, you know, land use, you had to log into a different system. So these were all disparate sources of data, disparate owners of the models and data. And so our job was to see if we can put it all together under one giant wrapper. And so from the modeling side, on the engineering side, we truly did apply a software engineering and model-driven engineering approach. We created the domain models, we created requirements engineering models, design models. All of this was actually model-driven. At that time, we used something called OMT, which is a predecessor to UML. So we truly did create object-oriented hierarchies, etc. But we also had to incorporate GIS system, georeference information, and also support simulation. And all of this had to look like it was just one system that somebody could sit down and pose some different kinds of queries and be able to reach out to all these different sources of information, right? So this is in fact what we resulted in, and that we have this Informs was the system that we built to support this data-centric approach to making informed decisions. Oops. And so lots of different kinds of data, right? So the data was georeference, time series, land use, biological. We had both types of models, the scientific models and engineering models. But the key thing was we were trying to support sort of the science-based questions, right? In order to form policies and look at the different kinds of socioeconomic impacts as well, right? And as far as the disciplinarity aspect of it, we started out as multidisciplinary. We each had our own respective expertise, right? But then by having this informed system, we were able to enable the scientists, the policymakers to really look at the interdisciplinary aspects, right, of making land use decisions and policies. So this is sort of, you know, at that time it was just like, can you even do this, right? And like I said, there was no Google at that time. There's no plugins. Distributed computing was still kind of emerging at that point. OO was sort of an interesting idea, but can we actually, you know, come up with a way to build real systems? And this, in the end, we built systems for the USDA, we built systems for the EPA, as well as NASA, right? And this was something that was essentially the same basic object-oriented architecture, but we made it such that you could actually extend it and be able to apply it to different data and different types of questions. And it turns out that the organization that supported this work is still active, live today. And in fact, if anything, making informed decisions is even more important, even more data. We have even more data and more models, right? And the impact is even greater. And I think the challenge is now with a policy analyst, you know, sometimes they'll just take the easy way. If you can get access to the information, fine. If you can't, then they just base it on whatever their staff will provide to them. So we didn't want to, you know, give them that kind of excuse. So even recently, with working with some of the same group from the MODA group, we were actually looking at how we can come up with ways to even more effectively help the different stakeholders in environmental science be able to better understand the impact of the models and the data. And so we came up with this kind of vision for model experiencing environments so that you could actually have a much broader community be able to look at the impact of different decisions, right? If I decide to go vegan, you know, what's the impact going to be? If I decide to, you know, take shorter showers, not water my lawn, what's the impact, long-term impact, short-term impact, right? And so the idea is that let's not just leave it for the policy analysts. Can we actually do this at a community level, maybe even at an individual level? So making access, right, to this information. It's a very disparate collection of information. So key takeaways, real world problems, accessing lots and lots of information and data models to enable informed decision making. So this was looking at land use policies. The bridges that we were looking at is multidisciplinary, both between engineering and scientific, but also interdisciplinary with the data and model integration. Outside the box, at that point, we were really pushing the boundary of MDE, really actually able to capture the notion of reuse, the portability, distributed computing, one-stop shopping. The key thing was that we wanted to enable the users to focus on the environmental science problem and not the technological issues underneath, right? So this idea is you can really focus on the decision-making pieces of it. And from the assurance perspective, clearly, if we can make much more informed decisions regarding the environment conservation, then that is going to definitely address assurance on a grander scale. All right, so then next we move, so that actually was looking at how we could integrate data and models, large collections and heterogeneous collections to help inform decisions. Now the next question is, can we take the basic same objective, but now to use it to drive the operation, right? The development and the operation of autonomous cyber physical systems. See, these are active systems that are trying to to satisfy similar kinds of objectives. So in this case, we're looking at sustainability systems. So kind of keeping the same theme, right, with our decision support systems. So this could be things like smart grid systems and smart farming. And again, we still have a large collection of data, a large collection of models. And so keeping in mind the motor framework, right? So the key thing here is that some of the original intent for the bridges was that we had traditional practices, right? So farming, we know a lot about farming, right? It's very labor intensive, but it's also, you know, where, you know, how do we know that we're not over irrigating or under irrigating, et cetera? How do we take into account, you know, the general conditions of the soil, the different kinds of soil depletions from different kinds of crops? So potentially with the traditional practices, you may in fact have inefficient use of resources, and there's a lot of uncertainty factors, right? And so, you know, in terms of zoning practices, you know, in terms of the impact of weather, was it a drought year? You know, are you in flooding conditions? And so the question is, can we somehow try to take these traditional practices that we do have a lot of experience about and information, and try to add some automation, right? Make them become more autonomous, right? So again, that's going to require a lot of extensive historic data. You need to have descriptive models about, you know, the nature of the environment, the nature of the objective of the farming, et cetera. And you want to be able to automate some of these tasks. So this is clearly going to be very much a data-driven type of system, right? And so the question is then, what are the ways that we can actually support that transition? So again, you might start with a multidisciplinary perspective. You know, you have the domain experts, whether this is going to be the farmer, could be the agronomist, or the, you know, the soil experts, right? They could be weather experts, et cetera. And then you have policy analysts, right? That might talk about what kind of land use that you are allowed to, what kind of zoning is it, right? Is it farmland, or is it residential, et cetera? And then we have those of us who are working in the MDE-based autonomous system space, right? So question is, you know, how can we try to get beyond the multidisciplinary aspect? So here, part of the context is that, and this is back to the bridges, is the notion of understanding the sustainability idea. So really it is in fact 3 different pillars. You need to look at the environmental aspects, you need to look at the economic aspects and social aspects. So if we want to support smart farming, you know, we know that it's perhaps going to be better use of the resources from the environment, but what's the social impact, right? Are you displacing farmers, right? Are you displacing, you know, the people who are making the farm equipment? So that also obviously has the economic issues. And so when you look at all 3 of these things together, we do look at the notion of sustainability. And so that collectively potentially gives a transdisciplinary interaction, right? Because you're really looking at the stuff, all the issues surrounding that cross section across all 3, right? And so, so when you talk about the sustainability, we can talk about sustainability systems, right? So these are actually where you might have these smart cyber-physical systems that are intended to support resource production, coordination, and management, but focusing specifically on the notion of sustainability. So that would be our smart grid systems, our smart farming systems, our smart homes, right? And so again, these sustainability systems are going to have lots of different kinds of model and data, right? And so, again, how can we bridge that together again? So the idea is that if we can have these different disciplines work together, then we can hopefully be looking at more of the interdisciplinary interactions. So we actually, a group of us have proposed this notion of a sustainability evaluation experiencer vision. So the idea is to how to systematically be able to integrate your scientific models and engineering models, not only for the decision making, but also even to drive the actual autonomous systems or the smart CPS systems themselves. And so this was, yes, you might have smart physical systems that we can talk about, but the idea is that now we want to be able to drive those smart physical systems with our social socioeconomic information, the scientific models, and also any of the data that we're collecting, whether it's satellite data, whether it's runtime monitoring data, the soil conditions, et cetera, right? And as part of that process is that you want to be able to have your stakeholders be able to explore the different kinds of models and the data so you can actually play some what if scenarios. What if I decide to have, rotate my crops? How should I rotate my crops? So what are the impacts, right? In terms of planting corn and then soybeans and then, wheat, right? So what if I switch it around? What are some potential fallout? And so all of this is intended to give more exposure, making the different stakeholders be able to make more informed decisions. And now all that information can then be used to drive the operation of our sustainability system. So the idea is that we want to be able to do this, be able to support all of this adaptation with informed decisions, right, at runtime. And so one example is a project that Benoit Comamel and his colleagues have done to work with farmers on trying to come up with a smart approach to irrigating farms, right? So the idea is that, again, they have all the different instances, all the different kinds of data, all the different kinds of models, but then being able to integrate that to drive the overall irrigation system itself. All right, so this is trying, and then at the end, the idea is you take these disparate data types, the different kinds of models, and potentially use the SEER framework to help us to come up with these data-centric autonomous cyber-physical systems. So here we have land use data, production and consumption data, you have socioeconomic data, again, the different kinds of models. We have the scientific models with the descriptive and analytics, and then the engineering models. Not only do we have the system design models, but here, importantly, because we are talking about autonomous systems, we also are thinking about the models at runtime, right? How are these going to evolve and respond to the changing conditions? And again, it goes back to supporting the specific problems, and that is science-based questions. How do we support irrigation from the perspective of sustainability in the context of the different policies for land use, and keeping in mind what are the different socioeconomic impacts, right? And so from here, the disciplinarities, we started out as multidisciplinary, we transitioned to interdisciplinary to try and address the management of these sustainability systems. So key takeaways, again, we're trying to access lots of disparate data and models to enable decision-making. In this case, that decision-making then is going to be used to develop and operate, right, these sustainability systems. So we're taking it one step beyond. And again, that disciplinarity is looking at the engineering, the scientific, and a key addition here is the using of the models at runtime, where we're looking at both historic data as well as the runtime data. And then I think that the key thing here is that transdisciplinary is this notion of the sustainability systems, right? We can actually make much more informed decisions for the purposes of sustainability. And I think that part of this is now that we're able to have much more sophisticated technology that hopefully enables a broader, much broader impact, right? So it's not, we're not just relegating this to some, to just a limited number of policy analysts, right? The idea is that you have now this infrastructure that you can now use to talk with your different stakeholders, right? And again, since we are still in the context of sustainability, assurances, if we can, food production is one of the #1 conditions for the whole world. If you just go online, you talk about smart farms, the people who are most interested are actually the folks who are in third world countries, right? Because this is a real day-to-day concern for them. And similarly, water quality, water use, right? I mean, so that's something that many of us take for granted as far as having access to that resource. And so if we can have much more effective and sustainable use of our two key resources, it is truly assurance, like our life depends on it. All right, so finally, I want to look at intelligent transportation systems. It's yet another data-centric autonomous system with lots and lots of different kinds of data, lots of different kinds of models. This one I'm posing more as more of an open issue, and this is why the question mark, how do we get there, all right? So one thing that, to kind of give us some context, it turns out, as you probably heard, there's a lot of buzz about autonomous vehicle. And for just a context, we can think about autonomy as 5 levels of autonomy. Level 0 is probably my car. I have no automation, no truck. I have brakes, I have steering, but nothing that's going to have the computer decide to control it for me. But now people you can go one step up and you have some kind of driver assistance, right? These are automated driver assistance systems. And so you might have things like collision avoidance, right? You might even have lane keeping. The key thing here is that not only are you detecting that you are potentially departing from a lane, it actually does mitigation. So there is actually autonomous control that's moving you back. You might, if you have a collision avoidance system on your car, if it detects that the obstacle is too close, it actually might invoke the brakes. It doesn't just sound an alarm. And then you go from there to level 2, which is partial automation. You have lots of, not just one type of automated task, but you might have multiple automated tasks. And this is getting closer to this notion of self-driving. But the key thing here is that human intervention is still needed. So there is this notion of a safety driver. Then you go to level 3, which is what they call conditional automation. So the idea is you are getting even closer to self-driving, right? But the idea is you're going to constrain the conditions and the context in which that might happen. So maybe it's going to be perfect weather, sunny weather, no clouds, no rain. Maybe you're going to have limited speed, right? You can't go any faster than 35 miles per hour. But here, even you still are assuming that you have some kind of human intervention. And it turns out that for those of you who are financially, how should I say, equipped, the Audi A8 apparently is one of the commercial vehicles that you can purchase. Otherwise, there are these other research cars like the Google car. And Tesla, I think Elon Musk just made an announcement a few days ago that apparently he's planning on having the Tesla also be able to support level 3 automation. Then you move into level 4 automation. It's full automation, and the idea is that you might have a driver or remote operator, maybe the driver sitting in the back seat, right? But the idea is that some entity has to still be able to take over. And again, it's going to have more limited context in which this can be used, right? Perfect weather and limited behavior in terms of speed. And then full automation it's completely automated. You could just plug in where you want to go and then just go. And this is the point where you might not even have any pedals or steering wheel. So this is what we have now, probably level 1, but maybe you probably have these kind of features. So you have like blind spot detection, you have some kind of rear collision warning system, lane departure warning, adaptive cruise control. And the question is, how do we get from level 1 to level 5, right? And so what kinds of outside the box thinking do we have to do in terms of the types of models? And I think that the interesting thing is, in fact, let me see if I can move my level 5 could look like this, right? Where you can see, I mean, for me, it looks like these people could be in a train car, right? But the idea is that they are, in fact, in individual mobiles, and all they had to do was plug in a destination, right? And as you see, there's definitely no pedals or no steering wheels. So the key challenge is that uncertainty is abundant, right? So the uncertainty in terms of the physical conditions and the environment, the human interaction, and now in this case, it's the interaction with other vehicles in the highways, right? So the key thing here is that even if we do deploy autonomous vehicles level 1 through 5, you're still going to have a lot of the non-autonomous, okay, or not smart vehicles, right? So these are the ones that are not talking to your car. So how do you design your autonomous vehicle to be able to interact with that, right? And there's lots of uncertainty with respect to the sensor technology, the communication infrastructure, right? Obviously, with all this autonomy, there's going to be a lot more communication, both in terms of the wireless, with the satellite, the onboard, and then you have all of the third-party devices, right, that have to be able to be factored into your system. And then the complexity, right? This is where the challenge is in terms of all the data that's being processed and all the different models that are being used to support the manipulation of that data. So the ecosystem that we have then is, in fact, you have the computing-based devices, right? You have the human-based factors themselves, right? In terms of whether you have the driver, pedestrians outside, you have the other drivers of the other cars, right? And then the environment itself. And so the forces that you have to think about is that they're all competing for the resources, whether it's the roadways, whether it's the communication infrastructure, right? And they're all just running, right? It's decentralized control. And clearly, assurance is essential, right? I mean, this is truly one of the big challenges. So this is where I make an appeal to you, right, all is, how do we model the elements of all the ITS systems, right, of the ecosystem and their interaction, right? So I think lots of us have worked in different parts of it, one individual vehicle or maybe an individual subsystem with the vehicle. But I think that most of us have been looking at it from more the engineering side of things, right? How do we build these systems? How do we enable them to be autonomous? And I think what I posit to you is that we have to think about all the human factors. How do we model the behavior of the other drivers, right? So in the US, you can get a driver's license when you're 16, but you can start driving when you're 14. So just think about that for just a second. Those of you who are not in the US. That's probably a very scary thought, right? Because you're having teenagers out there that are operating these vehicles. At the same time, we have different auto insurance rates, right? If you're under 25, it's extremely expensive. I think it can be up to $700, $1,000 every 6 months to pay to insure a driver who is younger than 25, right? And why, right? Because the idea is that the experience level, the kind of decision making that the younger drivers might have might be different than more experienced seasoned drivers. So how do we model that information, right? Because that information is what we're going to have to use to counter, that's going to be part of the environment for our autonomous vehicle, right? So how do we model that kind of cognitive behavior and that kind of decision making? And so similarly with pedestrians, right? How do we model the behavior, anticipated behavior of pedestrians, right? How they might interact with our autonomous vehicles. And same thing goes to bicyclists. And so these are all challenges in terms of when we're trying to design our autonomous system to be able to respond to these different kinds of scenarios and contexts. Similarly, the environment, right? What kind of road conditions? If I train my vehicle to operate in Michigan, we have pretty challenging road conditions, especially if we've had a bad winter. We might have huge potholes, right? And so if you trained your car to operate in California and then you bring that car over to Michigan, you will not be able to handle the potholes, for example. The roadway infrastructure, right? The lanes themselves, if you have lane departure, what happens if your lanes are actually, your lane markings are no longer visible? The environment with respect to the weather, if it's foggy, then some of your sensors like LiDAR don't work, etc. So these are all modeling challenges, right? And the thing is that we can't model everything. So how do we choose what aspect of our environment to model, what aspect of human behavior to model, right? And then from there, what kind of data are we going to collect? How frequently are we going to collect it? How much data is necessary? How much data is needed, right? And then how do we integrate the data? How do we integrate the models themselves, right? And so as we've all probably noted is that right now, not just our software engineering or research community is really looking to AI and machine learning as dealing with a lot of our challenges, but somehow the non-computer science side of the community has caught on. And I think that they are all looking for that silver bullet, what's going to help us deal with the challenges. And I think that because in general, AI and machine learning have been sort of recognized as dealing with uncertainty, I think a lot of the stakeholder community has decided that they can handle all types of uncertainty, right? And I think that that's the one misunderstanding and misconception of the community. But unfortunately, the cat's out of the bag. We have politicians who are saying, hey, we're ready to roll out, level 3, level 4 autonomous vehicles in a few years, 3 or 4 years, right? It's a little bit scary. But as our keynote, Yashua Benjo said yesterday, what's missing in the current machine learning arena is this ability to understand and generalize beyond the training distribution. So there's limitations that are going to be imposed by the training data. So if you hadn't considered it, it's not going to magically somehow be able to know about that. And so that kind of goes back to my question about, well, what data is it that we need to be collecting? What data are we trying to monitor, right? And how much of it do we need so that we can actually inform our models themselves, right? And so one of the key messages that I got from listening to Yashua's talk yesterday is that we need to be able to support conscious processing, right? And that is what humans use when they're faced with unexpected and novel situations. And I think at least in the space of autonomous vehicles and intelligent transportation systems, that is going to be probably true for, for the near future for our generation, because there's so many different kinds of scenarios and so many different kinds of contexts, right? How do we deal with that and capture and address that with our different kinds of models, including machine learning models? And one question he asked, how can, well, I asked the question, what is the role of software engineering for AI? And I think that that's something that we have an obligation and a responsibility to make, if the community, different communities are going to embrace AI and ML for so many of their challenges, then how can we as a community support that to make it more systematic, right? And do it in a more robust and resilient fashion. And clearly, assurance is going to be a significant challenge, right? Just because it's not just, now it's no longer just your one vehicle, right? You have a whole ecosystem, right, of vehicles that if you have, if you've overlooked, certain kinds of constraints and issues, you're going to deploy it to thousands of vehicles, right? And how do we account for all those different scenarios? And not to make life even more difficult, but recently I've been doing work with the automotive industry on dealing with cybersecurity, and that adds a whole nother level of complexity to the assurance of autonomous vehicles. And then finally, autonomous systems and intelligent transportation systems is not just a technical challenge, right? It's really more of a socio-mobility challenge, and that goes back to our human factors. And so we have to look at that from the big picture perspective. So I just give you kind of a shout out. So hopefully, where I'm looking forward to Christoph's talk tomorrow about trying to address some of the challenges associated with the models that use AI systems for autonomous vehicles. I think that he'll point out some of the advantages and disadvantages and how we can kind of overcome some of the big challenges. And I'd probably give us some more marching orders about how to do that. In terms of the role of SE for AI, I wanted to point you all to a talk and also some papers that a colleague of mine, Tim Menzies, has been working on, and you'll see some of the different special issues that have come out recently. But I mean, just beyond optimizing AI models and extensibility, here's a longer list of where software engineering could help AI, right? The configuration, the maintenance of these systems, interfacing to other software. We talk about the testing aspects. How do we talk about the assurance of the AI models themselves and the AI techniques? How do we certify AI-based systems? And there's a whole area called assured autonomy, right? Looking at assurance of systems that have learning-enabled components, right? How do we make them more usable? How do we package? So at the end of the day, Tim's takeaway message there is AI needs software engineers, right? So there's lots of room. And I think I would go one step further and say we need not only software engineering, but model-driven engineering expertise. So for me, I've been working on the assurance for autonomous systems for many years, but I think that the one thing that I wanted to point out in terms of not only just adaptation and verification tactics, but like I said, I came more from the formal methods community, but I realized it was hitting a lot of stumbling blocks and obstacles by just using traditional techniques. And so in an effort to form a bridge, I was able to reach outside of my comfort zone, outside of my box, and be able to leverage techniques coming from the search-based community, looking at evolutionary-based techniques to help us to overcome some of the obstacles that traditional formal methods and formal assurance techniques might pose. So all these different techniques that we've developed have that kind of characteristic, is that they have the formal reasoning capabilities, but then they're going to be coupled, right, and synergistically complemented by using search-based techniques to expand the scope and the utility and applicability. And then more recently, looking at MDE-based assurance for cyber-physical autonomous systems, right? Looking at feature interactions, to mode discovery, how do we support robustness and digital twinning of cyber-physical systems, looking at also non-functional cases. Again, they have that same kind of characteristic. We have the formal reasoning supported, but we also complement it with a lot of the search-based techniques. And I do want to kind of call your attention to some recent work that we've done with one of my students, Michael Langford, where we're looking at uncertainty exploration in the context of machine learning and cyber-physical systems. And so here again is trying to look for some of the gaps or some of the, that you might have with some of the training data with an eye looking at how we can identify data and conditions and contexts that would potentially be detrimental to your system, right? So the idea is to try and help make our cyber-physical autonomous systems more robust and resilient. All right, so one area that is a new area for me, and it's probably, again, the bridge, is looking at socio-mobility, right? And this is really looking at the intersection of engineering and social sciences and looking at the societal implications of looking at mobility, right? Such as self-driving cars, and so again, we always, for those of us in the software engineering community and model-driven engineering, we tend to look at the technical side, but this is really forcing me to look at more of the sustainability issues, right? And some of the socio mobility aspects of it. And so we're looking, I have a new project working with, again, people from a whole slew of disciplines, from traffic management to sensor technology, to business, to law, to health, and so on, looking at what are some of the society impacts, right, of autonomous transportation, right? And legal inspection. If you get into an accident, whose fault is it? Can you blame it on the computer? If you have a safety driver, is it the safety driver? So many of you might be familiar with the recent accident with the Uber driver. And there was, a lot of attention paid to say, oh, look, this is a failure of the technology. And eventually they found out that, in fact, there was some software flaws with the system, but at the end of the day, they did not blame Uber. They actually have now charged the driver, the safety driver, with negligence homicide. So here's the challenge, how are these, we're almost like we're forming laws as we speak, right? Because we're sort of reactive to the impact of the autonomous transportation. All right, so I'm going to go back to real world problems as takeaways, the bridges, outside the box, and assurance. And so I wanted to show you, this is a picture that my son recently took because he's got this fancy camera as far as his pandemic hobby, and he was focusing on the birds, right? That was like a really cool thing to see. Apparently that particular type of bird, I don't know if it's a sandpiper, I'm not exactly sure. But then after, when he was uploading his pictures, he realized that in fact there was a shark in the background, right? It was really close, relatively close to the shore itself. So this is my cautionary tale that we get focused on the shiny stuff. We have these autonomous systems, these self-driving cars. Wow, that's great. But let's be wary of some of the assurance concerns as well, right? So I want to just give a shout out to my my motor group again. So this is, you saw we started out on the beach, but this is a recent e-happy hour that we had. This is our new normal. So this is a list of all of the different participants, and this is only one screen capture. But at the end of the day, we're still smiling, so that's a good sign. And then I wanted to close with the ultimate human bridge. My dear friend and colleague, Robert France, passed away a few years ago, but he was the one who kind of mentored me about really the importance of all the different bridges that we build to the people in our community. So I realized recently, the last couple of years, that some people may not actually know him, had not met him personally. So there's a couple of papers that have been written about his work, both from the research perspective as well as his contributions to the technical, or to the education side of things. Okay, with that, I will close.
Okay, thank you very much, Betty, for this very nice talk. So I'm going to applaud, and maybe others can applaud as well. Thank you very much. And yes, if there's one takeaway from your talk, it's building bridges, basically, right? So, so we've had quite some activity in the Q&A, and some questions were asked and upvoted. I remind you, you can always ask your questions, and people can upvote for your questions, so they come in first. So the first one is from Lionel Briand. Since we cannot prove safety for such systems, we can only collect evidence the system is safe, for example, through testing, certification, etc. enforcing good practices, gaining confidence, and hope for the best. How can we determine whether the risk is acceptable? The very notion of acceptable risk is contentious. So do you have any insights on this?
Thank you, Lionel. In fact, this is an area that we are actively working on. So the whole, with the area of assured autonomy, when you have systems that have learning-enabled components, to get the federal government, for example, to actually even buy into that, they have this whole push on notion of certification. So in fact, what kind of evidence is sufficient for a given stakeholder to actually trust this? And so I think that we can collect, like you said, all this evidence, and I think at the end of the day, there needs to be sort of almost a remake of what we consider how we do risk analysis, right? What kind of risks are we willing to take, right? And depending on which stakeholder community you're coming from, you may have different risks. This is why I'm saying that the whole notion of autonomous mobility is it becomes a socio-mobility issue. So that's why the stakeholders, like our legal experts, our business people, right? All of these people will actually have to come together and come up with what is in fact deemed acceptable, right? And so as somebody pointed out to me, they said, we have car accidents every day, right? And different people or different entities are blamed for it, but we don't stop all driving when we have a car accident. But on the other hand, when that Uber accident happened, they took all of their Uber vehicles out of commission, right? And so the idea is that there is this tendency to be very reactive, to say, oh my gosh, yes, people kill in car accidents, but once a computer does it, now we have a real problem. And so I think that is sort of, it's still a mental model shift at this point. And I think that there has to be, if you will, no pun intended, but I think there has to be risk models developed, right? Collecting lots of data and figuring out exactly, what are the trade-offs that are being made, right? Are there more lives being saved by having autonomous vehicles versus, not? And I think that those studies have, I hope they're being done, but I'm not sure, because I feel like right now there seems to be this race to try and get who's going to be the first OEM to get the fully autonomous driving out there. But I think that we do need to take a step back and look at more the socio-technical aspects of it, the socio aspects of it. And so and part of the challenge is that there's messy things like politics that have to be thrown into it, right? And so so I don't have a clean answer for you, Lionel, but I think the point is that though we need to create models, right, and collect the data to try and address those, explore what if scenarios, right? What level of autonomy? I think I mentioned to you on the level 5, there were discussions that it's possible that you might see that within 10 years. That means that the technology has to be ready in less than 5 years. And to me, that's not really reality at this point. But anyway, so, but I think that the key is that we can bury our head in the sand and say, no, it's not going to happen. Or we can try and take an active stance in it, right? And so we need people like yourself, Lena, and your group trying to look at different ways we can address assurance. But there is no one way to do it.
All right. Great. So we have time for a few more questions. So the next one is from Edouard Bateau. Can sustainability systems be sustainable? So yesterday in the keynote, Yoshua Bengio mentioned how AI is greedy, and he would like to add that hazards induced to social systems by powerful surveillance tooling such as smart grids, etc. So how can sustainability systems be sustainable?
I think that that indeed is hopefully that should be the objective. And I think that part of the challenge is that if you want to take a look specifically at those that have AI-based technology, that's where the software engineering I think has to come into play, because that's something that we can actually help them with. We've been building systems for decades, right? And so why should AI based systems be that much different? In other words, can't we still apply a lot of the software engineering principles, right, to make those systems also sustainable? And I think that there are trade-offs, right? I mean, there's whole workshops or groups that look at sustainable systems in general, right? How to make them sustainable. But I think that we should not treat AI-based systems as something that cannot be helped, right, in terms of software engineering based capabilities, software based technology. So I think if we want to try to actively address the sustainability of such systems, that we do need to look at more of the software engineering based techniques, right, and think about what the trade-offs. Do we have to always retrain our machine learning algorithms from scratch if we discover some new type of condition or new type of pattern, right? Is there a way that we can make this much more incremental, right? And so I think that there are strategies for doing that. But again, that's going to require our bridges. It's going to require the different kinds of disciplinary work, right? And also thinking outside the box, right? How can we apply what we've done with sort of our traditional software-based systems and apply it to our AI-based systems?
Great. So the next question is from Michalis Famelis. And it's related to, you know, the SEER you have talked about, where there's decision making to be done. So two of the key principles of the Montreal Declaration for Ethical AI that Joshua mentioned yesterday are democratic participation and non-repudiation of responsibility. These sound like principles that we should also be taking as first-class concerns when modeling for decision making. Where are we in terms of state of the art for supporting them?
I wish we were further, right? I mean, I really do feel like we're in a state where we are so rushing to reach technological milestones that we haven't spent enough time. And I maybe I should just say for myself that we have not spent enough time about looking at the societal impacts, you know, and then the responsibilities themselves. And so that's why I think that why one of my key messages is to promote the notion of bridges, right? To work with colleagues, to work with the stakeholders who do study societal impacts, right? Look at the ethical issues, right? And so he talked about using, you know, machine learning for good, right? And so, you know, it's reality, right? You do it for good, and then you realize that somebody's exploited it. So how can we think about that ahead of the game, right? Rather than trying to go back and try to put things back into the Pandora box. And so I think that in order to address those questions, Michalis, is that we need to be reaching out now to our colleagues who are studying this. So it turns out, because of my new project with looking at socio-mobility, I've met a whole community of people that's their whole purpose in life, is to look at the societal impacts of autonomous transportation. Imagine that. I mean, so I'm actually the resident engineering person that's supposed to be coming in and talking about, and then they ask me, you know, when is this going to happen? When is the autonomous vehicles going to be unleashed? And, you know, is it safe? And I have to be the Debbie Downer. I have to actually say, no, I don't think we're ready. And so I have, part of the people are saying, well, I'm representing the people in the elderly community who might be otherwise, you know, not able to be mobile. So they are really depending on the autonomous vehicles. In fact, I was supposed to give a talk at our local, they have AARP, American Association of Retirement Persons Community. I was supposed to go give their lunch talk, talking about the future of autonomous mobility. And all these people are expecting them to be able to now be able to go to the grocery store, go to the doctor's appointments all on their own without having to rely on taxi services or relatives. And I had to say, well, we're not quite there yet. We're not ready for that, right? And so I think that there are these ethical issues and the responsibility issues that we do have to think about. And I think that we can think about them by first reaching out to people who are already working on these areas. And then we need to inform them to say, hey, this is what's happening. This is what's possible. You know, what are some things that we need to also be thinking about as we come up with the technology?
Great, thanks. So the next question is from David Benavides, who's actually joining from SPLC, because I remind us that this is a shared keynote with models and SPLC. So David's question is, do you think that with the advent of data-centric applications, big data, the paradigm of building software-intensive systems will take a turn to more data-oriented programming or modeling rather than object-oriented programming or modeling? In such a case, maybe features would represent both worlds.
Sure. I mean, I think that for me, data-centric and object-oriented are not that far apart, right? Object-oriented is supposed to be sort of data-focused, data-centric. I think that the key challenge here is In this case, maybe the one difference is the volume of data, right? And the disparate nature of the data itself, that might make it more complicated. So I think that the key thing is that the data is not only about historic data, but also what you can capture at runtime, right? Because that will directly have an impact on how the current systems themselves are operating. So that perhaps is one of the one difference. But yeah, no, I mean, I think that whatever we can do to focus on the problems, right? And not just on the mechanics of it. And I guess one thing I would go one step further, it's not just the data, but it's how we actually are manipulating that data. How do we transform that data, right? From data into knowledge, right? And knowledge into algorithms, or you know, all the way up to gaining some insight about how these systems work. And so that's that transformation. So whether it's collecting features together to be able to look at, you know, down the road capabilities. Yeah, but I think that we're not that far off.
So we probably have time for 2 or 3 more questions. So the next one is from Lidia Fuentes, and it's more related to energy efficiency. So do you think it's a good idea to include the energy efficiency as a design and runtime goal, generating some code that consumes the least amount of power? Do you think more should be done on reducing the energy consumption of code, such as in security, video compression, etc.?
Absolutely. I mean, there are already people who are looking at that, right? They call it green technology. And so I know that at ICSI, they have a sustainability track, or not sustainability, but sustainability for, I don't remember exactly the acronym, but that's what they do, is that they're all focusing on how you can make technology more green, right? I mean, looking at how you can make algorithms more efficient, right? And how you can, you know, in general, it's all about the footprint that your technological systems are taking. And so there's actually quite a bit of focus on that. And so it's not just about batteries, right? It's about the algorithm, the software itself, how it's designed, how it's extended, how it's maintained, how it's monitored. Yes, so yes.
Right. So the next question is from Bedir Tekin asking more related to the third part of your talk. So modeling autonomous systems requires many different unforeseen combinations of the reality constraints, like system 2 thinking that we heard yesterday, beyond the known distribution, which is not easily tractable. So general purpose static models might not suffice, and we might need models that are more domain specific and generated at runtime. Is that true? Can you comment on this?
Sure, absolutely. I mean, I think that in general, static models, they definitely have a purpose, right? They can help us do a lot of things in terms of reasoning and in terms of the actual design, the predictive nature of those. But I think, as I said, one of the key bridges, right, moving from the traditional systems to autonomous systems is in fact the use of the models at runtime, right? And so that can in fact include using the models, but actually revising, updating the models. The models themselves become adaptive at runtime, right? And so as part of that, you know, can they in fact be generative in nature? Why not, right? I mean, I think that also there is a notion of, you know, how things like reinforcement learning can be brought into the fold. And so, yeah, I think that there is more need to look at what can happen at runtime in a reactive nature to what's going on in the environment. But I do want to make sure that we still stay tethered to our assurance concerns, because especially if your question is in the context of autonomous transportation, is that, you know, we can adapt and we can change and can respond, but let's make sure that we keep in mind what are some of the assurance constraints, so that there is some kind of bounding, right, in terms of that. And so, but I think that as these models might change or might generate, we do need to think about, you know, how they are at the end of the day still enabling our systems to deliver acceptable behavior. May not be perfect, but it's acceptable in the context of the uncertainty in which it's responding to.
All right, great. So that's all the time we have for the questions, but there's a lot more questions there. So we're going to create a discussion group in Wova so that they can ask questions, and it will be dedicated for your talk, and you can answer the questions live there without any problem. So with that, we thank you a lot, Betty. So thank you very much, and another round of applause. And
thank you.
yes.
So I have homework. You say I have homework now. Thank you all.
All right, so this puts an end to the keynote, and now we're gonna go to the next session, which is the award session, still in this room.
Okay, so welcome all to the award session. We will first present the awards, the different awards of this Models edition, and then we will present certificate for recognition of service. So let's start.
Okay, so thank you, Juan, for the introduction to the session. So it's an honor to be able to give this award. But before I give this award, and since I won't have the chance to say this at the banquet, because unfortunately there's no banquet this year, I really want to express my deepest gratitude to Eugene and Hoari. It's not a surprise if I say that this has been the most challenging Models conference ever. And they had to basically replan the whole conference just a few months ago when we decided to go virtual. So in the name of the whole Models community, I really want to thank you, Eugene and Hawari, once again. A special thanks as well to Sebastian, who is basically the person with the team of volunteers making sure that we are actually able to speak right now. So thanks also, Sebastian. And let me also take this opportunity to announce that maybe they got infected with the virus, but Eugene and Juari decided to be brave enough to propose themselves to host Models again in Montreal. So in 2022, we'll try to go back to Montreal this time for real. So thanks again.
Thank you very much.
Yeah, thank you, Jordi.
So now let's move to the most important award that the Models community can give, the Career Award. And to be honest, I'm a little bit scared to give this award to the awardee, Jean-Marc again, because maybe you are too young to remember this, but he was the steering committee chair of the UML conference in 2004. And that was the last time that conference took place. Fast forward to 2020, we decided to give the award to Jean-Marc in February, and in March we were confined and Models had to go virtual. So I don't know, but I'm starting to see a trend here. So Jean-Marc will give the Career Award talk next year in Japan. So good luck in Japan in 2021. But now let's really get serious. So let me read what the Model Charter says about this award. So according to the Model Charter, the goal of the Career Award is to recognize long-standing scientific and leadership contributions in the MD community and to identify role models for the more junior members of the Models community. Well, I don't really think I need to justify why Jean-Marc fulfills this criteria, but I will try. So Jean-Marc is a full professor and director of IRISA since 2012. IRISA is a research lab unifying, very typical in France, the forces of CNRS, ENS, INSA, INRIA, Telecom Bretagne, Central Supélec, the University of Rennes, and the University of Brittany in computer science. So basically he needs 2 slides just to complete to put all the logo for the affiliation. And clearly Jean-Marc has done it all in the research world, and especially in our research field. He has been the general chair, he has been PC chair, he has published over 200 papers in this and other conferences with very relevant contributions, especially in the field of executable modeling. And Kermeta is probably one of the tools that you probably remember. He has also been leading for many years one of the most well-known research teams in NDE, has written books, supervised plenty of PhD theses and industrial projects, and he even has a YouTube channel. So you may want to take a look at that as well. Or I don't know, maybe you can also find him in TikTok doing dance challenges. I didn't check that one. But Jean-Marc is clearly an inspiration for many of us. He is always open to mentor and give career advice. He has done it for me, and I'm sure he has done it for many others listening now. So for all this, it is my absolute pleasure to give Jean-Marc the Career Award of the Models Conference Series, joining Brand Selig and Robert Franz as the only 3 people that have received this award. So congratulations, Jean-Marc.
Thank you very much for that. So I don't know whether you hear me.
Yeah.
Yes.
Okay. So thank you very much. I'm extremely moved by what you said, because as Betty said, Models is really also my family. I was there at the very first UML conference in '98 with a paper there, and coming from the same background as Betty and the formal modeling stuff and showing how you could use formal techniques to validate UML models, basically. I could not attend because it was the birth of my last daughter, so I had to cancel my participation at the last minute. But I was part of that, and I was a program chair of the UML 2002 and steering committee chair when we decided to change the name of UML to models, actually, and to show that it was not just one modeling language, but it was the process of modeling that was important. And of course, since 2012, I was less involved with that because I was basically dean of the computer science department of the universities and all these organisms in Iran. But my term is nearly over. I will end it in December, so I'll be free again to do research, and I hope to join back my family and participate again to the Models Conference. So I'm extremely proud and happy to be given this award, and extremely thankful to the Models community at large, because again, as Betty have shown, research is mostly a cooperation process where people join, talk, and discuss and bring new ideas by cooperation and discussion with other people. And I think that in the Models community, we have that in several places, including at the conference when we can interact physically. And I hope next year we can start again that. And I think that's one of the great community for this cooperative process of doing research. And again, thank you very much to everybody to have done that, because it's not just my work, it's the work of many people and the community at large.
Thanks.
Thank you.
So the next award, oops. Sylvia?
Yes, hello everyone. It's my honor and privilege to announce the recipients of the Models Most Influential Paper Award from the past 10 years. This is an award that recognizes the achievements and contributions of people in our community. In my role as the Vice Chair for the Models Steering Committee, I have been asked to lead the selection of the paper that end up receiving this award. This was not an easy task because there were several excellent and high quality papers presented at Models in Oslo, but the selection committee agreed that this paper had something special because it not only presented a sound contribution from the academic and scientific point of view, but it also a contribution that has had a great impact in terms of industrial adoption. As in previous years, I prefer not to disclose the name of the senior members of our community that helped me in the selection, but I would like to thank them very much for their input and support. And now, without further ado, the 10-year Most Influential Paper Award this year goes to Gabor Bergman, Akos Horvath, Ethan Hall, Daniel Varro, Andras Baglog, Zoltan Baglog, and Andras Okros for their paper on incremental evaluation of model queries over AMF models. Congratulations. And finally, I just want to invite you to attend the MIP session tomorrow morning at 10 a.m., where the authors will share their insights about their paper and reflect on the impact that it has had on the field. Thank you.
So the next awards will be presented by Juan de Lara.
All right. Since Models is an ACM 6 of sponsor conference, then we can provide, of course, 6 of awards. So these are awards that are regulated by the ACM, for which we can designate a small percentage of the full papers accepted in the foundations track. So the criteria was based on the scores of the reviewers, the strong and weak points identified in the reviews, the comments from the program committee and program board members, and a poll among the committees who had the opportunity to vote. So this year we have 2 awards, and the first one is presented to Wael Kesentini and Bahis Alizadeh for the paper Interactive Metamodel Model Coevolution, a clustering-based multi-objective approach. Congratulations. And the second award goes to Jean-Olivier Ringert and Syed Waki Wali for the paper Semantic Comparisons of Alloy Models. Congratulations as well. So we will make sure that you receive this prize by email and physically. And by the way, both talks were presented yesterday, but if you didn't have the opportunity to see them, there's no problem because they are both recorded on and accessible through WOBA. Okay, we also have an overall prize for foundation track papers, which is kindly sponsored by Springer with 250 euros in books within their collection. And the awards goes to Jean-Olivier Ringert and Syed Waki Wali for semantic comparisons of alloy models. So congratulations.
And now it's my great pleasure to announce the Best Paper Award for the Practice and Innovation track. This award has been selected based on the reviewers' feedback and scores, as well as nominations received by the program board members. And the award this year goes to Hui Song, Rosten Dalvod, Nicolas Ferry, Arnold Solberg, and Frankie Fleury for their paper on model-based automatic fleet deployment of edge computing applications. Congratulations.
Right, so the next award is for the Best Tool Demonstration Award. It is selected by the Tool Demonstration Chairs, Benoit Combemal and Manuel Wimmer, based on the score and reviews, the quality of the provided video, and the novelty and potential impact. And so the award goes to the paper called Papyrus for Gamers Let's Play Modeling by Antonio Bucchiaroni, Maxime Savary Leblanc, Xavier Le Palec, Jean-Michel Bruel, Antonio Cicchetti, Jordi Cabot, Sébastien Gérard, Hamna Aslam, Anapoli Marconi, and Mirko Perioli. Congratulations to all.
All right. So this year we had excellent reviews and a high involvement of the program committee and program board member, despite the difficulties of the COVID. So we are truly thankful for them. But we wanted to recognize the work of members that produce exceptionally constructive and detailed reviews and have particularly high involvement in discussions and decision making. So we'll present this award to one reviewers in the foundation track and also in the practice and innovation track. So in the foundation track, it is presented to Jürgen Dingel. Congratulations, Jürgen, and we are really thank you to you and all the program committee members, of course.
And now it's my pleasure to announce the Best Reviewer Award for the Practice and Innovation track that this year goes to Bram Selig from Malina Software Corporation, Canada, for his outstanding job in reviewing the papers for the track. And thank you, Bram, for your detailed and very constructive feedback to the authors.
So congratulations to all the winners. And now we will move to the recognition of service certificates. People who did a really huge job for the conference, especially this edition, because they have to adapt to unexpected circumstances. So let's start with go ahead.
So the first recognition of service certificate goes, of course, to our dear PC chairs, Silvia Abrao and Juan de Lara, for the fabulous work they have done for this program. They've treated over hundreds of reviews, monitored over thousands of exchanges during the reviews, and significantly helped us in preparing the program of the conference and input on virtualizing the conference. So thank you very much.
We also want to thank Sebastian Moser for the huge amount of work done, first with the student volunteer, but more importantly, in the last 2 months with the virtualization of the conference. So thank you, Sebastian.
The next one is for the workshop co-chairs, Mathieu Hacher and Nelly Bencomo. They were extremely proactive and we really appreciated their effort to manage the 11 workshops, their speakers, the organizations during the first 3 days of the conference. So thank you very much.
Okay, our special thanks also go to Richard Page and Iris Reinhardt-Berger for sharing the tutorials and for being very proactive for setting this very interesting program. Oops.
And we thank the tools and demonstration co-chairs Benoit Combemal and Manuel Wimmer for running the tools and demonstration tracks and allowing us to have fantastic presentations of the modeling tools integrated within the program this year.
Many thanks also to the poster chairs, Jamaluddin Khaladi and Farhad Khandaq, for their contribution to Models 2020.
I'd like to thank Hussein Ergin and Matthew Steffen for their work as artifact evaluation co-chairs and making sure the research papers are backed with correct tools, data, and empirical proofs that and that the work is presented is reproducible. So thank you for all you have done.
Thanks also to Daria Bogdanova and Michaelis families for their work on the setting of the Educator Symposium.
So special thanks to Manar Al-Alfi and Jürgen Dingel for chairing the doctoral symposium and running it and organizing one of the most fruitful one in terms of participation.
Thanks also to Nancy Laramé and Daniel Varro for the huge work they did for setting up these industry days inviting people, many meetings, many discussions. So thank you all.
We'd like to thank Davide Di Lucio for running the ACM Student Research Competition, which actually, although we did not have enough submission to have it as an official competition, he kept on pushing forward to make the SRC happen. And he made sure that the submitter lived the experience of a real student research competition. So thank you very much for that.
Thanks also to Esther Guerra and Ludovico Jovino for the proceedings. This year was, they did a huge job also collecting, verifying, setting everything, preparing. So, so many thanks for them.
We thank Zhenzhang Hu for chairing the panel, which will happen after the second break today, and also for preparing next year's edition, which will be announced tomorrow. Thank you.
Thanks again to Michaelis families for the publicity chair, for sharing the publicity and coordinating with the regional publicity chairs. This was really one of the nice idea we had this year to try to disseminate the model through all the continents, and the participation show us that this was a very, very good idea that we recommend to maintain. So thanks you all for your participation.
Yes, and thank you to Huisong, who was the social media chair and kept everything active and tweeting and Facebook. So thank you very much for your help there.
Thank you, Jörg, for putting in this conference some human interaction despite the distance between people. And I participated at least in 2 sessions, and it was really amazing how people was engaging. And so thank you, Jörg.
Yes, and just to remind you that these sessions happen on the last break of every day. So thank you, a special thank you to Linda Lamar, who's our finance chair and works in the department of the computer science department and operations research at the University of Montreal, and who is making sure that all the finances are taken care of. So merci beaucoup, Linda.
Thanks also to our web chairs, Eric Raichan and Manusher Sadame. So thank you a lot.
And last but not least, this conference wouldn't be running without the team of student volunteers running around and hosting all these Zoom sessions. So more specifically, we thank Manel Abdellatif, Hyacinth Ali, Aaron Babiakian, Oussama Ben Sayer, Mouna Dawadi, Yann Gauthier, Amene Kazamiraki, Louis-Edouard Lafontaine, Shihab Mukaddam, Halves Nicasio, Corinne Pulgar, Rijul Sayani, Bashirman Singh, Martin Wesso, Mohamed Amin Zaheri, and Zahra Variamini Meheri. So sorry for mispronouncing some of the names, but we thank you very much.
So this ceremony is over. We thank you all for attending the keynote and the ceremony. Enjoy this the coming break, and hope to see you in the next coming sessions.